So my crazy idea is the Big Bang and a remote future, they seem completely different. One is extremely dense, extremely hot. The other is very, very rarefied and very, very cold. If you squash one down by this conformal scaling, you get the other. So although they look and feel very different, they're really almost the same. The remote future, on the other side, I'm claiming is that where do the photons go? They go into the next Big Bang.
Welcome to the Cosmic Frontier. Today, we're diving into an astonishing discovery by the James Webb Space Telescope that's reshaping our understanding of the universe. Join me on a journey through the cosmos as we explore James Webb's breakthrough in revealing the multiverse, breaking the Big Bang. My revolutionary concept revolves around the Big Bang and the distant future. At first glance, they appear starkly different. One is characterized by extreme density and heat, while the other is vastly spread out and incredibly cold. However, when we apply a technique known as conformal scaling to compress one, a surprising similarity emerges. Despite their contrasting appearances and characteristics, they are fundamentally akin. Particularly in the distant future, there arises an intriguing question: what becomes of the photons? My theory posits that they venture into the next Big Bang. For centuries, the enigmas of the cosmos have held our fascination, from the vast expanse of space to the minutiae of subatomic particles. Our journey of discovery continues to reveal astounding secrets, often upending our current cosmic comprehension. A crowning achievement in this quest is the James Webb Space Telescope, humanity's most advanced celestial observer. With a series of remarkable successes, this telescope peels back layers of the early universe, offering us unprecedented, crystal-clear glimpses into the cosmic past. This formidable astronomical tool holds the potential to detect light from alternate universes, thus propelling us closer to grasping the true essence of our own universe and pondering the existence of countless parallel universes. Join us as we explore the profound impact of the James Webb Space Telescope on our understanding of the cosmos. As we gaze into the cosmos today, peering beyond Earth's confines, a magnificent and comprehensive vista of the universe unfolds before us. We've come to understand that our planet, much like others scattered throughout the cosmos, is constructed from atoms. Encasing its solid core, made up of dense, heavy atoms, is a gaseous atmosphere. This leads to a sort of onion-layered structure in terms of composition, a pattern consistent across investigated planets, dwarf planets, and moons. Planets either drift freely in the galaxy or orbit stars, which themselves are remarkable forges, transforming lighter elements into heavier ones within their cores. The life cycle of a star is fascinating. When it depletes its fuel, the core contracts and heats up, potentially sparking the fusion of heavier elements, or transitioning the star into a remnant, either gently or through explosive events. On a grander scale, stars cluster together into galaxies, which in turn form groups, clusters, and even larger superstructures. Collectively, they create what is known as the cosmic web, characterized by galaxies strewn along filament-like structures, converging at junctions, and interspersed with vast cosmic voids. Understanding the current state of the universe is one thing, but unraveling its history requires the application of physics. We use the laws of general relativity to explain the role of gravitation, driven by mass and energy. Electromagnetism plays its part through charged objects and electromagnetic waves. Then there's the intricate workings of nuclear forces, from the binding of quarks and gluons to form protons and neutrons, to the assembly of atomic nuclei and the radioactive decay of unstable ones. By applying these principles and observing the evolution of these systems, we can start to piece together not just what the universe is, but how it came to be, governed by the timeless dance of physical laws. When a physicist is presented with initial conditions describing a system, they can formulate equations to predict its evolution. Within the bounds of natural uncertainty, and indeterminacy, these equations can forecast the probable outcomes of the system at any future point. So, how did everything originate? A logical starting point is Earth, bustling with diverse, sophisticated life forms, encompassed by an atmosphere, oceans, and a structured interior comprising a crust, mantle, and both outer and inner cores. At its simplest, Earth is composed of atoms. But delving deeper, it's a rich tapestry of elements from the periodic table, predominantly iron, oxygen, silicon, magnesium, sulfur, nickel, calcium, and aluminum. These are notably heavier elements, contrasting with the lightest ones, hydrogen and helium. Yet, when we explore the universe, hydrogen and helium are ubiquitous, accounting for over 99% of its atomic composition. The remaining fraction consists of heavier elements. So, for a planet like Earth to emerge, rich in rocks, metals, and complex molecules, there needs to be a mechanism to forge these heavier elements and then amalgamate them in sufficient quantities to form planets. Fortunately, our observations of the universe reveal these very processes in action. Within stars, nuclear fusion melds lighter elements into heavier ones. As stars approach the ends of their lifespans, depending on their mass, they evolve into red giants, playing a crucial role in this cosmic alchemy. In the twilight of their existence, stars undergo unique nuclear processes, different from those during their prime. They develop powerful winds capable of shedding significant portions of their mass. Their eventual demise may lead to the creation of a planetary nebula, with the remnant core condensing into a white dwarf. Alternatively, they might perish in a core collapse supernova, leaving behind either a neutron star or a black hole. These remnants, be they white dwarfs or neutron stars, can sometimes collide, sparking reactions that yield an even greater bounty of heavier elements. This stellar life cycle aligns with our observations. Star populations with fewer previous generations, like those in the Milky Way's outer halo, exhibit lower concentrations of heavy elements. Conversely, regions where stars have undergone multiple generations, such as near the galactic center, show higher concentrations of these elements. Moreover, recent direct imaging of protoplanetary disks around new stars has revealed gaps and clumps, suggesting the formation of young, nascent planets. These new generations of stars and planets are born from the recycled remnants of their predecessors, carrying the essential building blocks for life. Our exploration of the distant universe reveals not only the evolution of element abundances, but also the transformation of galaxies themselves. In our cosmic neighborhood, we observe large spiral and elliptical galaxies, densely clustered with low star formation rates. These galaxies possess significant mass, relatively little gas, and a higher ratio of red to blue stars. However, as we peer further back in time, we witness different stages in the cosmic saga, offering clues to the grand narrative of the universe. As we observe galaxies situated increasingly further away, two key differences become evident. Firstly, the more distant a galaxy is, the less evolved it appears. It's generally less massive, less clustered, and exhibits peak star formation that occurred around 11 billion years ago. These galaxies are rich in gas, have lower concentrations of heavy elements, and a higher proportion of blue stars compared to red stars, unlike the galaxies we see in the present day. Secondly, the light from these distant galaxies is systematically redshifted to longer wavelengths, a phenomenon known as cosmological redshift. When we incorporate general relativity into this observation, it leads us to a monumental conclusion: the universe is expanding. This expansion is the reason for the cosmological redshift observed in light traveling through intergalactic space. Consequently, galaxies that are farther away exhibit a larger redshift, appear to be receding from us more rapidly, and crucially, are seen as they were in a more distant past due to the finite speed of light. The growth and evolution of galaxies over time implies something profound. If we look back far enough, we might discover the earliest stars and galaxies, and beyond them, a universe devoid of such structures. This expansion and cooling of the universe, coupled with increasing gravitational clumping, suggests that the universe was once smaller, denser, hotter, and more uniform than it is today. By extrapolating backwards and applying relevant physics, we arrive at remarkable predictions. The universe develops structures like galaxies, galaxy clusters, and the cosmic web through gravitational growth within an expanding universe. There exists an epoch when the first stars and galaxies formed. Prior to that, there was only pristine gas, and even earlier, a period when the universe's radiation was so intense that it prevented the formation of stable atomic structures. The early universe was so hot that neutral atoms couldn't form. Consequently, there should be a distinct marker from the time when stable neutral atoms first appeared. Even earlier, the intense heat would have prevented the formation of stable atomic nuclei. As the universe cooled past this threshold, we expected to see specific elemental abundances resulting from fusion reactions in the universe's infancy. These predictions have been confirmed, along with many others. We've discovered a residual microwave radiation only 2.7 K above absolute zero, aligning with the anticipated afterglow of a hot Big Bang. Evidence has been found for the earliest clouds of gas, consisting solely of hydrogen, helium, and traces of lithium. Moreover, we've indirectly detected the predicted residual background of neutrinos and antineutrinos, evident in the large-scale structure of the universe and the temperature variations in the cosmic microwave background. The observed universe's characteristics suggest it was born with the seeds of its large-scale structure, a spectrum of regions denser or less dense than average. What could have created these initial variations? The answer lies in the theory of cosmic inflation. This theory not only provides a mechanism for generating these primordial fluctuations, but also explains the universe's observed properties and makes new predictions about the nature of these fluctuations. The theory of inflation proposes that before the hot Big Bang, where matter and radiation filled a hot, dense, and largely uniform universe rapidly expanding, the universe was actually devoid of matter. However, this emptiness was not devoid of energy. It was filled with a tremendous amount of energy inherent in the fabric of space itself. As the universe expanded, more space was created, maintaining a constant energy density. This process imprinted the universe with uniform properties, stretching it to such an extent that its curvature became flat. The tiny quantum fluctuations, which are normally present throughout space, were amplified by inflation to enormous cosmic scales. According to inflation theory, these stretched fluctuations should have created the initial seeds of today's cosmic structure. They would have had properties such as being nearly the same in magnitude across all scales, generated on scales larger than the cosmic horizon, 100% adiabatic, meaning constant entropy, and 0% isocurvature, constant spatial curvature. The theory also suggests that the leftover glow from the Big Bang should indicate a maximum temperature significantly lower than the absolute maximum, known as the Planck temperature. Unfortunately, our understanding of the universe's origins hits a limit at this point. The nature of inflation effectively erases any information that existed in the universe before it occurred. We can only hope to understand events during the final 1032 seconds of inflation. Anything earlier than that remains beyond our reach. While we can confidently trace the origins of our observable universe and explain many phenomena within it, the very earliest moments remain shrouded in mystery. The unresolved questions about the origins of space, time, energy, and the laws of physics themselves, or even if they had a beginning, continue to challenge scientists. In response, they have devised various theoretical scenarios. Among these, some have gained notable recognition within the cosmology community, including Roger Penrose's conformal cyclic cosmology. Penrose's early interest in cosmology was piqued by the philosophical aspects of the steady-state model. This model suggested an infinite and boundless universe, continuously creating hydrogen, thereby allowing endless expansion. Despite its visual appeal, the steady-state model eventually fell out of favor when Einstein's equations were applied to cosmology, paving the way for the Big Bang theory. Both Penrose and Einstein initially leaned towards the concept of an eternal universe. However, the discovery of the cosmic microwave background radiation provided substantial support for the Big Bang theory. Penrose acknowledged these findings and the limitations of the steady-state model, recognizing the Big Bang theory as essential, particularly with the inclusion of inflation to complete the theoretical framework. Penrose has also contributed other intriguing ideas about the universe, including his perspectives on cosmic inflation, the expansion of the universe, the role of black holes, and the universe's eventual fate. Regarding cosmic inflation, Penrose describes it as a cosmological theory that seeks to explain the universe's rapid expansion in the initial moments following the Big Bang. This theory posits that the universe experienced a phase of exponential growth driven by a force known as the inflation field. Cosmic inflation has been instrumental in clarifying various aspects of the universe's early development. In his study of the universe, Penrose observes key phenomena such as its vast structure and the uniformity of the cosmic microwave background radiation. He notes that while inflation theory explains certain aspects of the early universe, it doesn't adequately address the low entropy state during that period. To fill this gap, Penrose introduces his own theory, conformal cyclic cosmology. This concept envisions the universe undergoing a series of epochs, or eons, each beginning with a Big Bang and ending with a Big Crunch, cyclically returning the universe to a state of low entropy. Regarding the expansion of the universe, Penrose points out that Einstein originally perceived the universe as static. However, the discovery of supernovae revealed its continuous expansion. Penrose describes this expansion as leading to a more isolated and mundane universe, where increasingly fewer events occur. He foresees a future where all stars extinguish, no new stars form, and galaxies' black holes eventually coalesce. This scenario leads to a universe devoid of new energy, characterized by darkness, coldness, and emptiness. Penrose highlights black holes as some of the most fascinating elements in the cosmos. Unaffected by the universe's expansion, these dense entities form from the collapse of massive stars and exert a gravitational pull so strong that not even light can escape. The complexity of black holes poses significant challenges to our understanding of the universe, and Penrose believes that further study of these phenomena could reveal deeper cosmic secrets. Penrose also delves into the enigmatic nature of black holes, theorizing their potential to engulf everything in their vicinity, including entire galactic clusters. This scenario could lead to a universe dominated exclusively by black holes. Over time, these black holes would gradually evaporate due to Hawking radiation, leaving behind a universe devoid of substantial matter. This hypothesis intertwines scientific theory with a philosophical perspective on the universe. As the universe continues to cool, it is expected to transform into a barren expanse, populated only by photons. However, given the relativistic nature of photons, they remain unaffected by concepts like boredom. In this vast emptiness, the universe might resemble an infinite void, defined only by abstract mathematical concepts like infinity. Penrose's theory challenges and addresses some limitations of the standard Big Bang theory, such as questioning whether the Big Bang was a true singularity, the origin of the Big Bang itself, and the horizon problem, which pertains to the uniformity of regions in space that have not been in contact since the Big Bang. While conformal cyclic cosmology offers intriguing answers to these questions, its accuracy remains a matter of debate. The mathematics underpinning Penrose's theory is sound, but this doesn't necessarily mean it mirrors reality. In essence, it could be an abstract mathematical construct with no real-world counterpart. The true test of any scientific theory lies in its ability to make predictions that can be empirically verified. If these predictions hold true, the theory gains support. If not, it may be disproven. An example of this is the steady-state theory, which was initially popular but eventually superseded by the Big Bang theory due to contrasting observational evidence. The steady-state theory, which posits that the universe as a whole remains constant and unchanging over time, gained popularity in the late 1940 and 1950s. Despite its initial appeal, it was disproven in the 1960s upon the realization that the universe is indeed undergoing change. Stephen Hawking described the steady-state theory as a good scientific theory in the vein of Karl Popper's philosophy. It made specific predictions that could be tested and potentially falsified. Unfortunately for the theory, these predictions were indeed falsified. Turning back to Penrose's theory, the current consensus is that there is no concrete evidence supporting it. However, this doesn't definitively rule out the possibility of conformal cyclic cosmology. There might still be undiscovered evidence that could validate it. Interestingly, we find ourselves in an unprecedented era of discovery, propelled by advancing technology. This allows us to peer back into the moments following the Big Bang and explore the universe in ways previously unimaginable. One of the most groundbreaking tools in this endeavor is the James Webb Space Telescope. Hailed as a time machine, the James Webb Telescope is revolutionizing our understanding of the universe's origins and evolution, from our solar system to galaxies near the dawn of time. In its first year of operation, every image captured has been a revelation, enabling scientists worldwide to pursue questions previously beyond reach. A key objective of the James Webb Telescope is to observe galaxies as they formed in the universe's first billion years. Early observations have already revealed a young universe filled with unexpectedly mature galaxies. However, to truly grasp the nature of the early universe, astronomers need more than images. They crave the spectra of these galaxies. This crucial data, obtained by dissecting incoming light into its component wavelengths, offers a wealth of information about these distant celestial bodies. Galactic spectra, which the James Webb Telescope began transmitting in earnest at the end of last year, are invaluable for two primary reasons. First, they enable astronomers to accurately determine a galaxy's age. The infrared light captured by James Webb is redshifted, meaning its wavelengths stretch as it travels through the expanding cosmos. The degree of this redshift helps astronomers calculate a galaxy's distance and thus the time when it first emitted its light. Nearby galaxies exhibit almost no redshift, but the Webb telescope can discern objects beyond a redshift of 5, dating back to about 1 billion years after the Big Bang. Higher redshifts indicate even older and more distant objects. Second, spectra provide insights into a galaxy's activities. Each color in the spectrum marks an interaction between photons and specific atoms or molecules. For instance, one hue might be from a hydrogen atom emitting light as it stabilizes after being energized, while others could indicate excited oxygen or nitrogen atoms. A galaxy's spectrum reveals its composition and the behavior of its constituent elements, and James Webb offers this crucial context for galaxies at unprecedented distances. As astronomer Anush Saxena from the University of Oxford remarked, the ability to discuss the chemical composition of redshift 9 galaxies is truly astounding. Galactic spectra are also ideal for detecting significant influencers of atomic behavior, such as giant black holes at the centers of galaxies. While black holes themselves are invisible, they're feeding on gas and dust tears atoms apart, causing them to emit distinctive colors. Before Webb's launch, astrophysicists hoped the telescope would help them spot these patterns and find early universes' massive and active black holes to unravel the mystery of their formation. When James Webb observes young galaxies appearing as red specks in the void, it frequently detects cyclonic activity at their centers. The most likely explanation for these tumultuous hearts is large black holes, with masses equivalent to millions of suns, stirring the surrounding gas clouds. This finding aligns with expectations, since Webb was partly designed to locate these ancient entities, the precursors to the colossal black holes that appear surprisingly early in the cosmic record. By studying these early black holes, Scientists aim to trace the origins of their massive counterparts and determine which of two competing formation theories is more accurate: rapid growth or being born large. Yet, the abundance of young, voracious black holes observed by Webb is also baffling, challenging existing theories about the development of stars, galaxies, and more. Typically, black holes form from very massive stars that exhaust their fuel and then collapse. Stellar mass black holes, which form from the gravitational collapse of massive stars, typically range from 5 to 100 times the mass of the Sun. In stark contrast, the supermassive black holes found at the centers of galaxies are significantly larger. For instance, the black hole at the heart of our Milky Way galaxy, known as Sagittarius AE, boasts a mass of about 4.3 million solar masses. Yet, even this is dwarfed by the most massive black hole discovered to date, TON 618, located at the center of a quasar and weighing an astonishing 66 billion solar masses. The formation of these colossal black holes remains one of astronomy's enduring mysteries. While it's conceivable that they grew from the merger of smaller stellar mass black holes, this theory struggles to account for the time needed since the universe's inception 13.8 billion years ago. The formation of such immense black holes in the early universe seems even more enigmatic. The James Webb Space Telescope has the capability to observe ancient galaxies that formed just a few 100 million years after the Big Bang. In a significant development published in Nature Astronomy, astronomers integrated observations from Webb with data from the Chandra X-ray Observatory. This collaborative effort led to the identification of the most distant black hole yet discovered. This black hole, located in a galaxy referred to as UH zone, lies in the direction of the galaxy cluster Abell 2744, situated 3.5 billion light-years from Earth. Data from the James Webb Telescope has unveiled. The galaxy in question is considerably more distant than the cluster, situated at 13.2 billion light-years from Earth. This means it existed when the universe was a mere 3% of its current age. Over 2 weeks of observations using the Chandra X-ray Observatory revealed the presence of intensely superheated gas emitting X-rays. Such emissions are indicative of a growing supermassive black hole. The light from this distant galaxy and the X-rays from gas around its supermassive black hole were magnified roughly fourfold by intervening matter in the Abell 2744 cluster due to gravitational lensing. This magnification enhanced the infrared signal detected by the Webb telescope and allowed Chandra to pinpoint the faint X-ray source. This discovery plays a crucial role in understanding how some supermassive black holes attained their immense sizes so soon after the Big Bang. Did they originate from the collapse of massive gas clouds, forming black holes with masses ranging from about 10,000 to 100,000 suns? Or did they evolve from the explosions of the earliest stars, resulting in black holes weighing between about 10 and 100 suns? Black holes face physical limits on their growth rate once formed, but those born larger have an advantage in reaching massive sizes more rapidly. Andy Ging from Princeton University, a co-author of the Nature Astronomy's paper and lead author of a new study in the Astrophysical Journal Letters that reports the galaxy's distance and mass, likens it to the growth of a sapling compared to a seed. Using a spectrum from the Webb telescope, the research team found strong evidence that this newly discovered black hole was born with a substantial mass. Its estimated mass, based on the brightness and energy of the X-rays, ranges between 10 and 100 million suns. This mass is comparable to that of all the stars in its host galaxy, contrasting with black holes at the centers of nearby galaxies, which typically contain only about 0.1% of their host galaxy's stellar mass. Given the rapid formation of this ancient supermassive black hole so soon after the universe's inception, its origin couldn't have been through the merging of stellar mass black holes. Instead, a different formation process is necessary, as indicated by advanced simulations. Early in the universe's history, simulations have shown the possibility of massive gas clouds collapsing directly into very large black holes, each with a mass approximately 100,000 times that of the Sun. These immense black holes likely evolved into supermassive ones through a combination of merging with other black holes and accumulating gas from their surroundings. Although we've discovered just one ancient galaxy housing a supermassive black hole so far, more are expected to be found. This is especially true given that the James Webb Telescope only commenced operations in the summer of 2022. The data, such as that reported in the recent study, will provide scientists with crucial insights into the early stages of the universe. Key questions remain, such as the chronological relationship between supermassive black holes and galaxies. Did galaxies form first and attract extragalactic gas that facilitated the formation of supermassive black holes? Or did the black holes form initially, drawing in the gas that led to the creation of stars and galaxies? Other important queries include the impact of the heat generated by gas flowing into early black holes on star formation, and the role dark matter played in these processes. The answers to these questions are gradually becoming clearer as we continue our cosmic exploration. That concludes today's episode. If you found it informative, please give us a thumbs up and don't forget to subscribe and hit the notification bell to stay updated on future episodes. Your feedback is valuable to us, so feel free to share your thoughts about today's content in the comments section. Your support is our motivation to keep producing quality content and to strive for continual improvement. Thank you for watching, and we look forward to seeing you in the next episode. Welcome to Blessovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blessovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe. Live Q and a Sessions with Experts. Your membership will grant you the chance to participate in live Q and a sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos and join us in unraveling the secrets of the universe. Become a Blessovia Science TV member today, and together we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comment.